All right, section 10.3 now gets into the calculus of parametric equations. And so we're going to start with what we had before. We have these two parametric equations. X of t is this, y of t is that. So let's go ahead and put those into our calculator. So I'll go up here, clear that out. We've got 2.3t squared plus 5.1t minus 3. And then for the other one, it's e to the 0.81t. All right, so those are ready to go. And we're doing this from 0 to 7, so I'll go to window and make that from 0 to 7. And we may have to adjust our x and our y in a little bit. For now, I'm gonna make them go negative 50 to 50. I have no idea if that's gonna be a good enough. In fact, let's just take a quick little graph. Okay, so it starts here and goes that way. I don't need the negative. Looks like I don't need either one to be negative here. So let's go 0 and 0 for that. But it does look like I might need more on this end. So I'm gonna go 100 there. Let's see what that looks like. Okay, and it looks like I need more on the y too. So this is sometimes just what you have to do, right? You just kind of play around. That should be good enough. It looks almost like an exponential. There, we'll stop there and then we'll see what else. The other thing you can do when you're making a window like that is to go to your table and then see, since we're going from 0 to 7, you can see my zeros from negative 3 and it goes all the way out. Ooh, we need to go 150 on the x and 300 on the y. So we'll go 150 on the x, 300 on the y. This will give us the full look of this graph. There we go. All right, now everything that we want to do is on that graph now. All right, so make a sketch of the particle's path. That's what we were just working on, right? It kind of goes like this and goes up. All right, where is the particle at 2.5 seconds? Easiest way to do that with the calculator is to go trace 2.5, and we are at 24.125, comma 7.576. Okay, it's the easiest way. Just put 1 into the calculator, or you can put 1 in yourself here and do it that way. All right, what is the horizontal velocity at 2.5 seconds? So since we're asking about how fast we're traveling horizontally, we're only really concerned about this equation here. In other words, we're finding the change in the horizontal, the change in x with respect to the change in time. Okay, now if you had to do that by hand, wouldn't be so bad. dx dt would be 4.6t plus 5.1, and we would take 2.5, put it in for t and calculate it. I want to show you how to do it on the calculator though. So two ways, since we're on the graphing screen, we can go second, calculate. dx dt is option 4. So I hit 4 and I type in for 2.5 seconds. dx dt would be 16.6. Okay. Or if you're on this screen, you can go math 8, the derivative of alpha trace, and now you pick your x option at t equal 2.5, and we get 16.6 that way. All right. So if that's the horizontal velocity, then the vertical velocity would be dy dt. Okay, again, by hand, dy dt would be the derivative of e. Now e is its own derivative, so we go e to the 0.81t times the derivative of the exponent, which would be 0.81. Okay, plug 2.5 in for t and work that out. If we do that on this screen, it's just as simple as the last one was. The only difference is now we pick y instead of x at 2.5. And we get 6.137. Okay. If we do it on the graphing screen, it's the same way. You go second, calculate dy dt at 2.5, and there's your 6.137. Okay. So simple enough. They might ask us for this. They might ask us questions about, are we moving to the right, left, up, down? Since the dx dt is positive, we are moving to the right. Since the dy dt is positive, we are moving up. Okay, so we'll interpret those for that. What is the speed of the particle at 2.5 seconds? So speed is the absolute value of velocity normally, except that we have two velocities. We have a dx dt, we have a dy dt, right? So the way to understand this then is to think of vectors. So dx dt is how fast we're traveling in this direction. Dy dt is how fast we're traveling in this direction. One thing you can do with vectors is you can put one on the other. We did this a little bit last year in pre-calc, right? So we're sliding that over and we're putting that vector on the end of this, and that creates then this resultant vector, okay? This is the actual like tangent line, if you will. And more importantly is this, if we take the magnitude, the length of this tangent line, that will give us the speed that we're traveling, because we're traveling 16.6 to the right, 6.137 up. We're going to go ahead and find that, and that's easy enough. It's just a little Pythagorean theorem. Our speed will be the square root of dx dt squared plus dy dt squared. So if I just go ahead, here I'll leave that formula there. So take our calculator and let's go ahead and do that. I'll grab that, squared plus that, squared, and then we'll square root that. And our speed then is 17.698. That's the overall speed we're traveling in space. We're traveling at these two speeds component-wise, like in this direction and in that direction, but overall, we're traveling on this path with that speed, okay? So that's one of the things that will be asked in parametric is what's our speed, right? We might be asked, what is the slope of a tangent line to the curve at 2.5 seconds? So in other words, if we come back to this idea, we might be asked, well, what is the slope of this line here? Well, the slope would be change in y over change in x. So the easiest way to think of that change in y over change in x would be to take the change in y, which is dy dt, over the change in x dx dt. And that should make sense because when you divide two fractions, you take the first fraction times the reciprocal of the other. The dt's would cancel, we get dy dx, right? So for us, dy dt was 0.81 e to the 0.81 t. dx dt was 4.6 t plus 5.1. So that's an expression for dy dx, okay? If we want, we can put 2.5 into it and then calculate it. So I'm gonna go ahead and just go up here. Our dy dt again was this, divided by our dx dt, which was the 16.6, and we get a slope, when evaluated at t equal 2.5, we get a slope of 0.36 or 70 if we round correctly. Now, I can get that from the graphing screen as well. If I go dy dx at 2.5 seconds, I get 0.36, that same answer. So the graphing screen will tell me that. The only thing, I don't believe I can do it on the math screen, because if you do this, you have to take the derivative with respect to time of one or the other. I can't do it both. So I'm not gonna be able to do that here unless I were to say, set up, you know, let's go derivative of y at 2.5 divided by the derivative of x. I mean, that would be a little more work, but would get us our answer if we do it this way, right? So that's our slope of our tangent line. So it says, what is the equation of the tangent line at 2.5 seconds? This doesn't change anytime we're doing equation of a tangent line. We need point, we need slope. The good news is we already have our point from earlier. We found that to be 24.125, comma 7.576. And we just found our slope to be 0.370. So y minus 7.576 equals 0.3700 times x minus 24.125. So again, doesn't change how we do it. Describe the direction from the particle that's traveling. So basically, again, we had this vector going this way, we had a vector going this way, and we said overall we're traveling like this, right? So what we would like to do is to describe that angle right there. So the best way to think of that is to look at your two vectors. Again, this is 6.137, this is 16.6. And so that's opposite adjacent. This angle, this divided by this would be the tangent. Or in other words, the slope of the line is equal to the tangent of theta. So theta will be the arctan, or the inverse tangent, of our slope of dy over dx, right? And we have to be a little careful about that because sometimes when we do an inverse tangent on the calculator, it gives us an angle that we weren't necessarily intending. This case should be fine because we're in quadrant 1 here, but you do want to be a little cautious there. All right, so if I go ahead, this is my slope. If I go second tangent of that slope, I'm gonna get 0.354. So we're going 0.354 radians. Now, that's true, but most of us don't really think in terms of radians when we think of direction, right? Degrees is something that we're a lot more accustomed to understanding. So what I'd like to do is to really have this be in degree. So one thing we can do, there's a couple things, but one is we can just go ahead and change back to degree for half a second. Go up here and try this again, and now it will give us 20.289 degrees, okay? The other thing we could have done, if we don't like switching because we don't want to get caught in degree mode, is we could have said, let's take this, and I'm going to try this, and go to angle and say I want it in degree. Let's see if that works. No, I thought maybe that would work. Never mind, we'll ignore I said any of that. All right, now, that's part of it. We have the angle, but we need to be able to express this. So when you think in terms of space, straight up is north, straight right is east, then south, and then west. This is how our directions typically go. And so what we have is 20.28 degrees towards the north side of straight east. So the way we would say this is we're heading 20.289 north of east. We're not going straight east, we're 20 degrees to the north of what east is. That would be the easiest way to express that. So usually we say it's one way, either north or south of straight east or west. Now technically we could have said this is about 70 degrees east of north. That's just not typically how we would say it normally. But that is correct, that's where we're heading. All right, another thing we'll be asked is an acceleration vector, okay? And that's maybe a new thing, but it's actually a very simple thing. When we do an acceleration vector, we take the acceleration in the x direction, we take the acceleration in the y direction. We just simply say what those values are. We write them down. So for us, we can do this by hand and just kind of do the second derivative and work it out. But if we want to do it on the calculator, what we're going to do is we're going to take the derivative of the derivative. And we'll do x first. And the first derivative, I want the whole thing. So I want the entire derivative for the first one. And then when we do the second one, I want that at 2.5 seconds, okay? And that gives me 4.6. So the second derivative at 2.5 seconds is 4.6. So what we're going to do is we're going to do a vector mark and put 4.6 in the first one. That's the x, okay? Now we'll go ahead and find the y, and we'll do it the same way. So actually, I can come up here and do the exact same thing, and all I have to do is change the x inside to the y. And we get 4.971. And what this tells someone is that we're accelerating horizontally at a rate of 4.6, and we're accelerating vertically at a rate of 4.971. All right? So they'll ask us for an acceleration vector. It's pretty simple. All right, so let's switch up our expression and we'll do a couple more things here. So we're gonna put this one in 10.2 sine of 0.13x, and we'll put in 0.5x squared minus 3x. All right, and so first part A says write an expression for dy dx and the second derivative. So we'll start with the first derivative, that's easy enough. Dy dx is equal to dy dt over dx dt. So that's going to be t minus 3 over, and we'll go 10.2 times 0.13. That's 1.326 times the cosine of 0.13t. Okay? So that is our expression. I want to make sure I have this in. Yeah, I thought I put an extra one in there. All right. So we're good there. That's our expression. That's what dy dx is, and it's in terms of time. Okay. Now, when you go to do the second derivative, intuitively you would think to just take the derivative of this. And probably since it's written like this, you would think to do quotient rule. And that is partly correct. Okay. The problem is that when you do, when you go to take the second derivative and you do the quotient rule, you're only doing this part right here. And that's going to give you the second derivative of y, but it will not give you dx squared on the bottom. Now, I know this is going to sound a little strange, but you'll get a dt dx. And in order for that to go away, what we have to do is divide by dx dt, because if you flip this, the dt's will cancel, and you'll get this dx dx or dx squared on the bottom. So we want to, this is just, again, one of the little things that maybe doesn't make a whole lot of sense, but we just have to remember to do it. If we are asked to find the second derivative of a parametric, we're going to do what our instinct tells us, which is to take the quotient rule. So that's the bottom times the derivative of the top, which is 1, minus the top, times the derivative of the bottom, which is going to be this 1.326 times another 0.13. So that's going to be 0.17238. And it'll be a negative because it's going to be the derivative of cosine. So that's going to change that to a plus. It goes back to sine 0.13t. All over the bottom squared. 0.13t squared. Okay. This is this part, right? But we have to now divide it by dx dt. Now the good news is that by dividing by the bottom, what really happens is we just add another one of these to what's being squared down here. And so while it seems like this is going to make things very complicated, it ends up not really changing a whole lot. We end up with this, the top part as we had it before, over the bottom to the third power now. Okay? And that would be our answer there. Now, how often do they ask us to do that? Every now and then. So we just want to be ready for that. At what time does the curve have a horizontal tangent line? So a horizontal tangent line is going to happen when the slope is 0, and that's going to happen when the top is 0. So for us, that would be at time 3. At 3 seconds, we're going to have a horizontal tangent line. So when you look at this graph, if we went ahead and kind of graph this out, and I'm going to have to change my window. I don't think we need quite as much in either of these directions here. Let's see if that's enough. Now, I'm going to go to table and see. So from 0 to 7 seconds, looks like 0 to 10 works for x. We're in the negative realm for the y. So let's go up to 10, and we'll go negative 5 to 5. All right, does that work? There we go. All right, so where do we have a horizontal tangent? You can see the horizontal tangent is right there, and if I hit trace 3 seconds, you see that we're right there at that horizontal tangent line at 3 seconds, okay? That's where our dy dt equals 0, and we have and you can even see that we have a switch in dy dt from negative to positive. That's because we're switching from going down to going up. So they'll ask us those kinds of questions too. Where do we switch from going up to down or down to up or right to left and things like that. And so we want to then look at our dx dt, our dy dt, and kind of work it out. Our vertical tangent line occurs when the bottom is equal to 0, when we have an undefined slope, right? And so for us, that would be when cosine of 0.13t is equal to 0. That would be when 0.13t equals pi over 2. And if I work that out, sorry, shaky cam there. If I work that out, let's see. Pi divided by 2 divided by 0.13. It's going to be at 12 seconds. So if I extend this out 12 seconds, all right, and let me see what the table suggests we have to have that at. At 12 seconds, we need to be up at 36. And so let's go 15 and 40, okay? So we graph this. Oh, I should go just a little bit further, sorry. Oh, that was the problem. There we go. So we're gonna see it now. It comes this way and curls back. So we said at a little over 12.8 seconds. All right, let's take that and store it into alpha A. If I go to my graph now and trace alpha A, you'll see that right there is where we have the vertical tangent line, right? And in fact, if we extend this out a few more seconds and go up a little bit higher, all right, you're gonna see it come this way. It's gonna turn, and it's gonna head back to the left. And again, if I trace alpha A, right there is where we have that horizontal, or that vertical tangent line, okay? So we can see where this thing turns from going down to up. We can see where it turns from right to left. We can make those predictions by looking at when the individual equations equal 0, or their derivatives equal 0. Okay. Now, equation of a tangent line at 5 seconds is something we've done before. I'm not going to do it again here on this video. Speed and direction, again, is something we did before. Just to reiterate, though, speed for this would be the square root of dx dt at time equal 10 seconds squared plus dy dt at t equal 10 seconds squared. Right, so that would be our speed. And then as far as the direction goes, find your dx dt, your dy dt, and see what that angle is. Okay, but we won't do that here. We've already done that on this video. Acceleration vector, again, is something we've already done. Find the second derivative, all right, at 20 seconds. Find the second derivative at 20 seconds. Again, stuff we've already done, so it shouldn't be a big deal. Okay, what we do want to do is kind of look at something a little different. There's going to be we're going to add a little piece to it here. So we've got this equation, x equals t squared minus t. Let's get that on our calculator. All right, so we'll have t squared minus t there, and then here we have t cubed minus 3t minus 1. Okay, and for the window, let's go say -5 to 5. I think that works for this. And we'll go -10 to 10. We may have to adjust, but we'll see. Oh, perfect. All right, we're looking for where does the curve cross itself. So it looks like it crosses right there. Let's hit trace and see if we can get to that spot. All right, so as I move time up, you see that there's the x getting closer and closer, and it looks like we're there at 2, 1. So where does it cross itself? It crosses itself at 2, 1. Okay, at what times is it there? It's at t equal -1, and then if we let it loop around this, it will be back at 2, 1 at t equal 2. So we got those 2 times, once on the way around the first time, and then it looped around and then the second time. All right, there are 2 tangents at this point. So I would kind of draw this in like that, okay? There's 1 tangent the first time you're there, it kind of looks like that, and then there's a second tangent that kind of looks like that, right? Write an equation for each one. So what we need to do is find the slope at each one. We have our point, right? The point is 2, 1. That doesn't change. What changes is the slope from depending on what direction we're coming at it. So let's take -1, time -1 first. So we'll do the slope. So dy dx at time -1 is almost 0. In fact, I think that's close enough that we'll say that slope is 0. We have a horizontal tangent going on right there, okay? And so y minus y equals slope times x minus x, and we get y equal 1. That's our tangent line for there, okay? For the other line, that was at t equal 2. So I'm gonna go calculate dy dx at time 2, and we get a slope of 3. So y minus 1 equals 3 times x minus 2, and we can leave that, or y equals 3x minus 5. That's this tangent line there, okay? So 2 tangents to the same tangent point, just at 2 different times, so from 2 different perspectives, all right? Now here's the new question though, and that is, how far does this particle travel in between these times? In other words, as it goes around that loop, how far does it travel? All right. Now we've done arc length before. We did it and it looked like this. It was the integral of the square root of 1 plus the derivative of the function squared, okay? We're gonna do something very similar. Our arc length formula will be the integral of the square root, but instead of a function squared, since we have 2 different functions, we'll do each of their derivatives squared as part of this. And this will look familiar because this is the speed formula. So we're integrating speed to find our arc length, all right? So for this particular problem, we will do the integral from time -1 to time 2 of the square root of dx dt, which was 2t minus 1 if we do it by hand squared, plus 3t squared minus 3 squared dt. All right. And on the calculator, we can either do that, or I can take the calculator and go math 9 from -1 to 2, the square root of math 8 derivative of x at t equal, and we want this t equal t, I want the full derivative squared, plus, and then we're going to do that same thing again, math 8 derivative of y for t equal t, whole thing squared dt. And this may take a little bit of time because there's a lot of calculations to do, but when we get our answer, that will be the distance all the way around this thing, 9.708. All right, that is our arc length. And that covers everything that we'll have to know on an AP test.